We have developed the extremely important representations of continuous time and discrete time systems. Okay, in terms of their unit impulse response, you have CT system, and the input is, if the input is del of n, and the corresponding output is called impulse response h of n. Sorry, this is a DT systems. If it is CT system, then the input is del of t and the corresponding output is h of t. So, in the discrete time representation takes the form of convolution sum. Okay, and that convolution sum is y of n is equal to summation over k x of k times h of n minus k. Okay, while in the continuous time counterpart is the convolution integral y of t. You simply replace the summation by integration, and the limit is from minus infinity to plus infinity. By the way, of course, here it is minus infinity to plus infinity, and then x of k is replaced by its continuous variable x of tau, and h of n minus k is replaced by t minus tau and d tau. That is all. This is called convolution integral. As already I pointed out that one consequence of these representations is that the characteristics of an LTI system are completely determined by its impulse response h of t and h of n. It is important to emphasize that this property holds in general only for LTI systems, as I said, okay, because this h of n and h of t, then this convolution integral formula and this convolution sum formula, this all are derived based on the linearity of the system and time invariance property of the system. Okay, so in linearity we used superposition and homogeneity, and also we used time invariance property. Now, let us look at some of the properties of this LTI systems. There are three important properties. The first one is the commutative property. Okay, so this is a basic property, and let us look at discrete time first. So, what I am trying to say is, you have take x of n and give it to the system, discrete time system, and the output is y of n, and this discrete time system has the impulse response of h of n. Therefore, y of n is equal to x of n convolved with the h of n. Now, the same system you take it, no, not same system. Now, take some other system whose impulse response is x of n and the input is h of n, then also you will get y of n, and this y of n is equal to h of n convolved with the x of n. Both are identically equal. That is what we mean by commutative property. Okay, and here this expression is equal to summation over let us say k is equal to minus infinity to plus infinity x of k h of n minus k, and here the same expression you can write like you put h of k as it is, and here fold it and delay it, tau minus t minus, sorry, I am sorry, n minus k, like this. Both are same, and you can easily prove also. Okay, this we already did in the one of the previous lecture. Let us say n minus k is equal to r, and substitute, you will get this expression. Okay, therefore, it obeys the commutative property. That means x of n convolved with h of n will be the same as h of n convolved with the x of n. That's it. That means what? The roles of x of n and h of n are interchanged. Originally, the input is x of n and the impulse response is h of n, and it gives rise to y of n. This will be identically equal to, now the input is h of n and the impulse response is x of n, then also it gives y of n, and this y of n will be equal to that y of n. No change. So this convolution integral will be the same as this convolution sum. Okay, the output of an LTI system with the input x of n and unit impulse response h of n is identical. If I put 3 lines, that indicates identical to the output, this output and this output, okay, of an LTI system with the input h of n and impulse response x of n. Okay, so for example, we could have calculated the convolution by first reflecting x of k, this one, first reflecting x of t to x of tau, x of k, then x of k to x of minus k, then x of k to x of t minus k, like this. In here what we did, h of t2 to h of tau, and then from there h of minus tau, and then from there, sorry, this is n minus k, then h of n minus k, n minus k. Okay, so we could have calculated this convolution by first reflecting this one minus, let's say x, I am sorry, again I did a mistake, this is not t actually, this is discrete time, no, x of n, x of k, and x of k to x of minus k, first reflecting and shifting x of k, then multiplying the signals x of n minus k, this one, with this one x of h of k, and finally sum them. Okay, sum the products for all values of k. So both are same, that's what we mean by. Similarly, for convolution integral, you can say the impulse response is h of t for continuous time, and input is x of t, the output is y of t, and this will be identically equal to, the whole thing will be identically equal to, input is h of t. Now let's say the system response is x of t, and now this is y of t, both are equal. Now here this is x of t convolved with the h of t, therefore integral of x of tau h of fold and shift d tau minus infinity to plus infinity will be identically equal to h of t convolved with the x of t. So integral of h of tau, but now this time you reflect the signal, then t minus tau, shift the signal, and d tau. So both are identically equal. That's what we mean by. Okay, so we could have calculated this convolution, I mean the first convolution, okay, by reflecting and shifting x of t, and then multiplying the x of t minus tau with h of tau, and do the integration from minus infinity to plus infinity over tau. Okay, so in specific cases, one of these two forms for computing convolutions may be easier to visualize, but both of them forms always result in the same answer. Either you can use this one or this one, any one. So that's it about commutative property. The second property is distributive property. So this property says that if you convolve x of n, okay, with addition of two other signals. Convolve x of n with let us say h1 of n plus h2 of n, then it is equal to x of n convolved with the h1 of n plus x of n convolved with the h2 of n. That's it. That means you take x of n, put the convolution with the sum of these two guys, h1 of n plus h2 of n. This will be equal to x of n, first you convolve with the h1 of n, then plus this is you first you do it, then the second one is x of n convolved with the h2 of n. That's it. This is what your distributive property says. Sum of two convolutions. Here only one convolution. And here two convolution operations. So that is sum of two convolution. Okay. So this is the distributive property, and the proofs as I said are extremely simple. One can easily prove it. Now let me give a little more interpretation about this property. So if I say h1 of n plus h2 of n, this will be equivalent to like two systems which are connected in parallel, like h1 of n, h2 of n. These two are connected in parallel. The output is given to the summer. This is the adder or summer, plus, and here also you put plus, and this is the output y of n, and the input is x of n. What is output here at this point? This point is x of n convolved with the h of n, h1 of n, and at this point what is output? X of n convolved with the h2 of n. So the distributive property has a useful interpretation in terms of system interconnections. Here the systems are interconnected parallelly. Okay, now here we considered two continuous time systems. This is CT1 and this one is CT2. Okay, these systems are interconnected parallelly. Okay, and whose impulse responses are discrete time system I have considered here. You can consider either way, this way or that. So let's say it is a discrete time system, this also discrete time system. Okay, therefore the final output is y of n is equal to x of n convolved with the h of n plus x of n convolved with the h2 of n. The same formula you can develop for continuous time system. So you take x of t, convolve with the sum of two systems, let's say h1 of t plus h2 of t, then this gives rise to equal to, this is equal to x of t convolved with the h1 of t, right, plus x of t convolved with the h2 of t, sum of two convolutions. So by virtue of the distributive property of convolution, a parallel combination of LTI systems can be replaced by a single LTI system, because again you are applying the superposition principle. So instead of the two blocks in parallel, then I can put h1 of n plus h2 of n, and the input is now x of n. Similarly for continuous time, this is for discrete time system. For continuous time system, you put h1 of t plus h2 of t. Now the input is x of n, then output is y of n. Y of n is equal to convolution of x of n with the h1 of t plus h2 of t. This occurs because of the LTI, linear time invariant system. Okay, so therefore LTI systems can be replaced by a single LTI systems whose unit impulse response is the sum of the individual unit impulse responses. So this is the individual unit impulse response of system 1 and this is the individual unit impulse response of system 2. And the next property is associative property. If you have a convolution of 3 signals, let us say x1 of n, x2 of n, then x3 of n, then this associative property says the order in which this is carried out is not important. Okay, in which order you are going to carry out. That is what it says is you take x1 of n, you first convolve with x2 of n and then you take this result and convolve with x3 of n. This will be the same as x1 of n convolved with first you convolve this will be the same as first you convolve x2 of n, then with x3 of n you take this result and then convolve with x1 of n, doesn't matter, then also it gives the same result. Or even you can do in some other way also, like like you can convolve x1 of n with x3 of n first and then you can convolve x2 of n, then also it gives the same result, it doesn't matter. So the order of convolution in which you carry out is not important. Okay, so x1 of n convolved with this guy is the same as x1 of n convolved with x3 of n and x2 of n. Either way you can write down. So this is called associative property. And one more point I would like to discuss, it is not coming under a property of the system, but a stability for LTI systems. What happened to my iPad? Here you go. Yeah. That's it. So it is coming under stability for LTI system. Before talking about this LTI system, let us try to understand a simple concept. Let us say my x of n is like this, some digression. So DIGRESSION, digression. Okay. So let us say at 0 I have a magnitude of 4, then at 2 I have minus 1, at 3 I have some other value 5, then at 2, at 3 I have, let us say, minus 5, no, let us say minus 2. So all some arbitrary thing, example I am taking, minus 2, then the third point, then I have 6 at 4, then at 5, let me take one more sample like this, 0 to 5, 0, 1, 2, 3, 4, let's say this is again 1 like this. Now let me define an accumulator y of n. This is summation of n is equal to 0 to 5 x of n. What is this? This is equal to sum of all the values, like x of 0 plus x of 1 plus x of 2 plus x of 3 plus x of 4 plus x of 5, right? So if you sum all the values, 4 minus 1 plus 5 minus 2 plus 6 plus 1. So this is equal to 4 minus 1 3, 5 plus 3 8, 8 minus 2 6, 6 plus 6 12, 12 plus 1 13. This is the answer. 7 5 10 13, fine. Now let me take modulus. Then what will happen? Mod of sigma n is equal to 0 to 5 x of n. So that means again you expand this expression, you put all these guys here, x of 0 plus x of 1 plus x of 2 plus x of 3 plus x of 4 plus x of 5, and then you take modulus. Then it is again 4 minus 1 plus 5 minus 2 plus 6 plus 1, take modulus, it is again plus 13. Just simply write 13. Now let me consider one more quantity, like y of n is equal to, you take this modulus inside the summation like this, x of n. Again let us say n is equal to 0 to 5. Now in this case what happens? It is mod of x of 0 plus mod of x of 1 plus mod of x of 2 plus mod of x of 3 plus mod of x of 4 plus mod of x of 5, right? So what is x of 0? X of 0 is 4, mod of 4. What is x of 1? Minus 1, mod of minus 1, plus what is mod of x of 2? It is 5, mod of 5. X of 3, mod of 2, okay, like that. Then mod of 6 plus mod of 1, like that. Now this is again 4 plus mod of 1 minus 1 is 1 plus 5 plus 2 plus 6 plus 1. Now all are becomes positive. So 4 plus 1 5, 5 plus 5 10, 12, 12 plus 6 18, 18 plus 1 19. Originally this result is like this. So y of n, if you write like this, k is equal to 0 to 5 x of n. If you take magnitude like this, then it is 13. But if you write like this, k equal to 0 to 5, then mod of x of n, then this is 19. Therefore this is bigger than that one, right? Therefore in general summation of k equal to 0 to n mod of x of n is less than or equal to summation of k is equal to 0 to n mod of x of n. So this is a inequality that we need to remember. So in this case, in the previous example, this case is we got 13 and here we got 19. You take any sequence. Sometimes very rare case it will be equal, that is why we put less than or equal to here, okay. This is less than or equal to, please remember. So this inequality we are going to use for stability for LTI system. Now recall the definition of stability. We said that a system is stable if every bounded input x of n produces a bounded output y of n, then we say that system is stable. Now in order to determine conditions under which LTI systems are stable, consider this input x of n, okay, and this x of n is bounded by its magnitude. Okay, so x of n is bounded in magnitude, so you take magnitude, and this is less than for b for all values of n. Let us say it is finite value less than infinity for all n. Suppose we supply this guy to a discrete time system, then I will get the output y of n, and the impulse response of the system is h of n. Now, what is y of n? Y of n will be the convolution sum. So, this is equal to summation of k is equal to minus infinity to plus infinity h of let me write, no problem, other way also I can write h of k x of n minus k. Now, what we said magnitude, okay, we need to obtain an expression for the magnitude of the output. So, this is a normal output. Let us try to find out magnitude of the output. That's what our definition says. Every bounded input in magnitude produces bounded output. So, the input is magnitude. So, we need to find out the output also magnitude. So, y of n in magnitude is equal to summation of k is equal to minus infinity to plus infinity h of k x of n minus k, you take magnitude. Okay. So, we already just now proved that the magnitude of the sum of a set of numbers is no larger, that means what, less than the sum of magnitudes of the numbers. See, this is the magnitude of sum of numbers. This one is magnitude of the let's say a minute, a set of numbers. Okay, and this one is no larger, that means what, less than or equal to, you first take sum, okay, k is equal to minus infinity to plus infinity, first take sum of the magnitudes of the numbers. Basically h of k times x of n minus k are the numbers, right? That's fine. So, that's what for this case we got 13 in the previous example, and this we got 19, therefore, that's what this always less than. Now, again this one is equal to sigma k is equal to minus infinity plus infinity h of k, split the magnitude, times x of n minus k. You can write like this. Now, what we said, the input is bounded. So, this is my input, right? The input is bounded to b. You can replace in the summation by b, like this. So, you can pull out the b from the summation. So, b you take outside, then k is equal to minus infinity to plus infinity mod of h of k, right. So, original your y of n, therefore, your y of n is less than or equal to this upper bound b times k is equal to minus infinity to plus infinity h of k, like this. Now, if this is mod of y of n, then if y of n, if you want as a bounded value, then anyway this is bounded already, no problem. Then this also should be bounded. Bounded means what? This thing should be less than infinity. It's a finite value. Bounded means what? Finite value. Therefore, finite value means k is equal to minus infinity to plus infinity mod of h of k should be less than infinity. That means what? What is the meaning of this expression? The left hand side must give rise to a finite value. That's what we mean by less than infinity. Okay, so we can conclude that if the impulse response is absolutely summable, see this is absolutely summable and it gives the finite value, because you are summing over the absolute value, magnitude value, that is why this is called a absolute summation. You can call absolute summation or magnitude summation, whatever it is. So if the impulse responses are absolutely summable, summable means what? It should give a finite value. Okay, then if x of n is bounded, its magnitude is bounded, and the impulse response also absolutely summable, then y of t is bounded in magnitude. Y of n is bounded in magnitude. See, there are some systems where the input is bounded but the output will not be bounded because of the instability of the system. Therefore, in order to get the bounded output, you should satisfy two conditions. The first one is input should be bounded in magnitude, that is x of n is bounded in magnitude. Also, we will not simply say h of n is less than infinity, but what we say is absolutely summability of this h of n should be summable. Okay. Therefore, this absolutely summability, this equation is a sufficient condition. Sufficient condition to guarantee the stability of a discrete time system. Guarantee stability of a discrete time LTI system. Okay. In fact, this condition also necessary condition. Okay, that we will show little later, maybe in one of our problem section. Because there are bounded inputs that result in unbounded outputs. Therefore, the stability of a discrete time LTI system is completely described by this condition. So, it is a necessary and sufficient conditions. The same analogy you can argue for continuous time system also. Like you have CT system and the impulse response is h of t and the input is x of t, the output is y of t. Y of t is x of t convolved with the h of t. Then you write in the convolution integral form h of tau x of t minus tau d tau, and you take the magnitude of this y of t, you take magnitude, then this is integral of h of tau x of t minus tau d tau magnitude. Then this will be less than or equal to integral of minus infinity plus infinity magnitude of h of tau x of t minus tau d tau. Now this is equal to minus infinity plus infinity h of tau x of t minus tau magnitude d tau, and we assume that the input is bounded with some value, let us say b. So h of tau b times d tau you can pull out from the integration because it is a constant, a number, upper bound number, h of tau d tau magnitude. So now the y of t is bounded by like this. Now if this has to satisfy, then let me write one more step so that you don't get the confusion. B times integral of minus infinity d tau. Therefore, your y of t magnitude is less than or equal to d times minus infinity to plus infinity h of tau d tau. Now, in order to get the bounded output, the input should be bounded input by b value, this b value, and also it is absolutely integrable. Okay, that's what we mean by. That means you are taking the absolute value of h of t, h of tau, you take absolute value and then do the integration. That is why it is called absolutely integrable. Therefore, the system is stable if the impulse response is absolutely integrable. The final point is the system is stable if the impulse response is absolutely integrable. For the discrete time case, it is absolutely summable. That's it. Therefore, minus infinity to plus infinity h of tau, take magnitude and then integrate with respect to tau, then this should be less than infinity. Okay, so there are bounded inputs that produce unbounded outputs. Therefore, the stability of a continuous time LTI system is equivalent to this condition. So, this condition is needed to test whether the test for stability. So, let me stop at this point. Thank you very much.